All right, so continuing with this simple linear regression activity, let's see where we got to last time. I think we just got to the Scrabble example. Yeah, we were talking about some of that. Okay. So yeah, as a quick refresher, we were looking at this data set on Scrabble letters. And so specifically, we were actually able to look at the entire data set because it's not that big. We have like each letter is a row in this data set, and then we have the percent relative frequency in English writing. So like how often the letter shows up in English writing. And then it's Scrabble point value. The idea being that Scrabble assigns higher points to letters that are harder to use in the game, right? So this is a great example for simple linear regression because we have two quantitative variables and they're likely related to each other here. So we were looking at using linear regression to predict or to model a point value for a Scrabble tile for a letter specifically using its relative frequency. Okay. And we just got to, okay, so yeah, we talked about how you can calculate the correlation between two quantitative variables, but this person shows all these different scenarios where you can get the same correlation, but there's very different patterns in the data. So it always has to be used with caution. And anytime a correlation is cited to describe the relationship between two variables, it really needs to be accompanied with a visualization because it only tells you a very small piece of like the whole picture. So good to just use it in tandem with a visualization like that. Okay. And so we were looking at this, yeah, Scrabble data. We had the SAS output. Zoom in a bit more here. It's still a little small, but okay. And here's a scatter plot of the Scrabble value and the relative frequency. So with scatter plots, the convention is always to have the response variable y on the vertical axis and the predictor variable, or the explanatory variable, in this case, relative frequency, on the horizontal axis. Sometimes you don't necessarily have a orientation that makes more sense than another, but in this case, it definitely makes sense that we're predicting the Scrabble value. Like that's determined based on how easy it is to use that letter in Scrabble play. So this way is the one way it makes sense in this context. Okay. And so yeah, linear regression involves finding this straight line of best fit. Probably ends up looking something like this in this case, that fits the trend in these data points. Okay. So already here, it doesn't look great because it's kind of non-linear, which is unfortunately many relationships in real life, but we're sort of continuing with it here for the sake of the problem. Honestly, if you remember back to was it ANOVA, when we looked at one-way ANOVA and we were looking at survival time of cancer patients and we had some trouble with assumptions, we did like a log transformation of the response. A log transformation actually improves that relationship here too, and then you can use linear regression after that. But we're not going to do that here for the first time looking at linear regression. That's how I would handle that in real life. Okay, but before getting into interpreting model output from fitting this linear regression model here, there's a few things we need to look at. The model assumptions are always something you should check, which we had to do for one-way ANOVA, the two-sample t-test as well. There's some additional steps that are needed to do linear regression besides just the formal model assumptions. There's also what we call influential points and outliers, okay, which is right where we left off last time. So I added in the guide for Stat 216 document just recently. So if you downloaded it, you'll have to like re-download it from Blackboard. A little section on outliers and influential points. And this is in the readings on the course schedule as well, but I sort of typed up some notes on it in here. So outliers and influential points are sort of two types of problematic observations or data points when fitting a linear regression model. Starting with outliers here, talking about what that means. So for every data point, we have a response variable y, and then we have a predicted response variable, which we denote with y hat. Y hat is what is, like, here's all the y's, the vertical height of these points. The y hats are given by our straight line of best fit that we fit to the data. Okay, all the y hats fall exactly on our estimated regression line like this. Okay. The residual values are the gap or the difference in height between the point and the line of best fit. Okay. So this one has a positive residual. All these points down here have negative residuals, okay, that are bigger in magnitude as they get further away from the line. Okay. Outliers are points that have a residual that's really big in size, really big in magnitude. Okay. That's like the formal definition of an outlier for linear regression. Again, this gets into like, I think sometimes there's the muddying of like everyday language, like when we say, oh, that's an outlier. You know, for different contexts, that means slightly different things. In regression, it's very formally, an outlier is referring to a point with a large residual in magnitude. Okay. All right. And so why does that matter? So outliers are problematic because it alters the amount of confidence in our regression line significantly. So if one point is way off, like let's say we had a point that was like, for some reason, here's all the other points, and then we just had one that was like way up here, and then we fit our regression line. It might not necessarily influence the slope of our line or even where it's placed too much, but what it does is it lowers our confidence in our predictions overall, because it sees like the data when describing it, it sees like, oh, this was way off. Our prediction was way off. So it'll affect our confidence intervals and p-values significantly. Versus if that point were not in the data set. So that's why outliers are problematic, because they distort our p-values or confidence intervals. It also affects some of the model assumptions as well, because we need normally distributed residuals. And so if you have one that's a large outlier, that affects that normality assumption. We can't, again, to emphasize, you cannot apply the central limit theorem in regression by just saying sample size is really big, so the normality assumption is fine. That's a common mistake. We need the residuals to be very much bell-shaped. Okay. So how far away from that trend of the rest of the points is far enough to consider a point to be an outlier? Well, that's a subjective thing, and there is not a consensus in the statistical community, I would say. But SAS, for example, let's see where SAS draws the line. Yeah, SAS draws the line at 2 for what we call the studentized residuals. Okay. So if you remember back to Stat 215, does anyone remember calculating z-scores? Yeah, okay. So studentized residuals, you can think of it like it's like a z-score of the residuals. It's a standardized residual value. Because in different contexts for different units of measurement, like 100 might be really big in one context, but then not another. You know, if you're talking hundreds of dollars, maybe that's big, but hundreds of pennies is a lot smaller. So because of units of measurement differing among different data sets, different contexts, we can standardize the residual values onto a sort of like level playing field by calculating studentized residuals. Okay. So in general, if a studentized residual is bigger than 2 in magnitude, so less than -2 or greater than +2, we'll say it's an outlier. Okay. And looking at the diagnostic plots here, so if we go to the SAS output, we get the same 3x3 grid of diagnostic plots that we've seen previously. We can look at these in the top right. We have our student. Okay, and you can also look at this plot because it's giving the same thing on the y-axis, but pretty much we're looking for if a point is above 2 or below -2. So here, do we have any outliers for the Scrabble data set? Yeah, we have one, and then this one's just hanging out right on the border, I guess. So, yeah, maybe 1 or 2, right? Yeah, how would you handle that in real life? Well, I would say it's somewhat a function of the sample size, in that if you have 300 data points and you have one that has a residual value that's bigger than 2 in magnitude, that's really not a big deal at all. It's not very concerning. If you have 15 data points and you have one that's bigger than 2 in magnitude, that's much more concerning because it has more of an influence or more of an effect on the p-values and confidence intervals. Okay. In this case, our sample size is 26. We have like the 26 letters. So to me, it's a little bit of a gray area. I would say I'm not too concerned about it. But in practice, you may consider like fitting a regression model with this value excluded. And then also maybe consider fitting the regression model with all the data points included and then see how much your results differ. That's like a practical way to approach it. Okay. But certainly it needs to be noted too, because often removing data values and fitting a model can seem kind of shady or, you know, questionable in practice, depending on the context, but it very much depends on context. So yes, I think we had a bullet that actually asked. Oh, I skipped to outliers first. Okay, so we're doing the outlier bullet first. So yes, there is one data point that has a studentized residual. I think that's a studentized residual. Yeah, our student. That's for studentized residual. has a studentized residual that is larger than 2 in magnitude. Does anybody know why it's called a studentized residual? No, that's understandable. Have you heard of the student's T distribution? I think we've talked about that maybe. So the T distribution is also called the student's T distribution because the person who published it originally published the results about it originally was working for Guinness, like the beer company, and wasn't allowed to show their methodology, but he still wanted to publish in a journal. So he just published under the pseudonym student. And so now all this stuff is named after student, like student's T distribution, studentized residuals, because this person working for Guinness couldn't say who they were because their work was confidential. Okay. So that's our meaningless factoid of the day. Okay, so yeah, pretty much we're just looking, does any point have a studentized residual larger than 2 in magnitude? Okay, and so outliers, in my opinion, are less problematic than influential points. Okay. And these are commonly mixed up. But influential points, if we look up here, influential points are data points that have a significant effect on our regression estimates. So the outliers affect our p-values and our confidence intervals. Influential points have a lot of pull or leverage on the regression line itself, which is why I think it's much more problematic because it affects all of your predicted values significantly. I don't have visuals in the guide document yet for it, but influential points typically have high leverage, we would say, which means, so if you have your regression line here, I mentioned this last class a bit, it's sort of like a seesaw where the more a point is to the middle, the less leverage it has in tipping the regression line. And the more you get on the outsides, towards the edges, either way, the more leverage a point has, and that it will pull the regression line more towards itself. Okay. So for example, here's how maybe the estimated regression line looks here. If we instead had a point that was like way out here. Oops. Let me draw out there. Yeah, there we go. Let's say we had a data point way out here. So it was like a really high, really common letter in English writing. Okay. This is an influential point here because what would happen is because it has so much leverage, it almost, especially when it's that high, it almost forces the regression line to go right exactly through it. And it happens at the expense of all the other points in the data set, which is usually not desirable. Right? Yeah, so it has so much influence and pull that it improves its own predicted value essentially a lot, but then all your other predicted values get worse. And that just happens due to the mathematical derivation of how the line is fit. Okay. And so notice, oh, I erased it too soon. Maybe I can undo it. No, I can't undo it. Okay. But notice how, okay, so I'll put that point back out there. And then, yeah, again, we have the regression line that goes through it. Okay, so notice how this point is really influential. You can have a point that's influential and an outlier. Is this one an outlier if this was our regression line here? No, actually its residual is really, really small. So it's not an outlier, but it's very influential. That's kind of a tricky part. Sometimes it feels like every point that's influential is an outlier or vice versa, but it's not the case. So this point is we'll say influential, but not an outlier. Okay. And then let's see, I'll draw in green here. Yeah, I'll draw in green a point that's an outlier, but not influential. Okay. So if you want an outlier that's not influential, you need it right in the middle of your X value, but then also like really far away. It's like up here. Oh, that should have been green. Oops. There we go. Okay. Here, there's a point that's an outlier, but not influential because it's right smack dab in the middle of the data set. So it actually won't affect the slope of the regression line very much. Okay. Right. Any questions about the difference between outliers and influential points? The ideas there. Okay. So other than looking at a scatter plot of X and Y, which kind of helps give us an idea if there's outliers or influential points, again, we have like these formal diagnostic plots that SAS gives us. Okay. So studentized residuals, our student is how SAS labels those. That's what we use to identify outliers. For influence, for identifying influential points, we will use Cook's distance measure, which is commonly just called Cook's D. So this quantifies the total change in the predicted values caused by this single point being included in the data set. And so we'll say for this class, again, there's really not a consensus on this one. I would say more so with the studentized residuals, like it's pretty common for people to use 2 as the cutoff. I was Googling this for a while and people have different numbers all over the place. But I found that Penn State, someone in their stat department there said 1/2 for Cook's D is the cutoff they use to decide if something's influential. So that's what we'll do. And you can see SAS draws the line like lower. That's what the SAS developers thought, I guess. So, but we'll say 1/2. So based on the Cook's D plot here, how many, if at all, influential points do we have? Just one, yeah. So if we like imagined drawing a line here, yeah, here is the influential point. And SAS is nice in that it tells you what the observation number is. That's the x-axis, so you could look it up in the data set. So like, for example, here, it looks like it's letter 5, which is E. That's weird. E. Yeah, it seems like the letter E. Curious about that. Let's look that up in the table. Does E have like a weird point value? Oh, okay. Okay, it's just E occurs so much. E occurs like so often, it thinks it should be worth less maybe, but it's already worth only 1 point. So that's kind of the constraint the Scrabble makers had, I guess, when they made that point value. Okay. Okay, so yeah, influential points. So yes, there is one. Looks D value larger than 0.5. So it is likely influential observation. And yeah, similar to the outlier, unfortunately, it's not super simple what you should do. I think to say you should always remove it is wrong. To say you should always just keep it in the data set is wrong. This is where, again, if you're doing like a scientific study, maybe investigating like something public health related or something that would affect people's well-being, I would maybe fit 2 models, like one with the influential point included, one without, and discuss how the results differ. If you're doing something like I've seen influential points when I'm predicting the outcomes of basketball games, right? In that context, because it's ruining my predictions to have that point in there, like there's maybe a really weird game where, like, I don't know, let's say like Rutgers beat Duke by like 35 points one game one year. It was like really strange, unexpected. That would be more of an outlier, I guess. What would be like an influential point? Maybe like an influential point would be like, well, let's just stick with that. Let's say there's one game that's really affecting all the predictions in my data set. Since I'm just predicting basketball games, I'll probably just exclude it and get better predictions from my model overall. And that's okay in that context. But yeah, if you're predicting, right, like lead levels in children's blood based on the amount of exposure in baby food or something, just removing a data point conveniently to get more results like you want is like not okay, right? So very much depends on the context whether you can just pick out values and toss them out or not. So always have to keep that in mind. Okay. So let's give a statement of the assumed simple linear regression model. And here's again where I think looking at the guide document is good and copying the blueprint model that we have. Let's go simple linear regression. Okay, here's our assumed model. So let's copy that. Okay. All right, so here's our assumed model. And so we just need to say, mostly you just need to update what X and Y are for that context. So in this context for the Scrabble data, Y is the jth so what is our response value here? Yeah, the point value. Yeah, the Scrabble file point value. Or Scrabble letter, I guess. And then we also know what N is in this case, right? 26, yeah. Thanks. It's always good to put that in there too when you can. And then the only thing you really need to update after that is, yeah, I mean, the 26 down here, and then the X variable. So X is the, yeah, is the jth, or we'll say like the percent relative frequency of the jth letter. So yeah, you don't have to change too much actually. Just copying that model statement from the guide document and tweaking those couple things. All right. So checking for outliers in influential points is necessary and useful when fitting a model, but also we have a set of formal model assumptions that we need to check too. So I have a whole section in the guide document about that. So all of these, it's quite a bit of assumptions now. Okay. So we must assume we have a random sample. This data set's a little bit strange because we have all those Scrabble letters, which is kind of like a, well, it's not kind of, we would call it a census, I guess. Like we have data on the whole population here. This is every letter in Scrabble. So yeah, we don't really need to worry about the random sample assumption. So so that assumption is met. Okay. But yeah, again, normally you would need, yeah, what does like a random sample mean? So a few different contexts. So yeah, thinking about again, like how, like I like to try and predict the scores of basketball games. I wouldn't want all the games in my data set to be games that Michigan State played in and no other teams. Like that would be only representative of outcomes for Michigan State. But if I'm interested in predicting all college basketball games, I should have games from all the teams like randomly selected. Yeah, if you're looking at the effect of a dosage of a new treatment you're trying out on people's blood pressure, and you want this to work for, say, everyone in the United States, you need like a random sample of people in the United States. So make sure you have people of multiple genders, people of different races, lots of things. That's something that has, that's something that's maybe overlooked, and that like I know we learned in our clinical trials class in grad school, like traditionally, for some reason in clinical studies, it was mostly men. And so the results don't extend as well to women always. And that was like a problem. So it's always good to make sure you can have like a really large data set, but it needs to be representative of the group you're targeting, or else your results maybe aren't as reliable. Okay, so it's an important assumption, kind of glossed over. Here it's okay for this data set. Normality of the residuals. So we will check this just like we did before, looking at the histogram and QQ plot, looking for the same things. Yeah. So let's look at our SAS output here. Okay, and again, the central limit theorem doesn't help us out. Yeah, so here it looks just okay. This is one where it makes me a little nervous. It's unimodal. How is it looking in terms of symmetry for the distribution? Yeah, it's a little skewed right, which is not great. And you can see that in the QQ plot, when you have like this upward bend like this, that tends to indicate, if we look at the histogram and QQ plot section here. Okay, I showed, yeah, when it's right skewed, when your distribution is right skewed, you get this upward bend in the QQ plot. We kind of see that here a little bit, but it's not the worst. So this is, it's halfway between okay and problematic, I would say. So yeah, what should we do there then? Well, yeah, this is where you could consider, when you have right skewed residuals, people often try a log transformation of the response variable and then model that instead. That can sometimes fix that issue. Like I said, we're not doing it here because we're just going to keep things a little bit simpler, but that would be the approach. So here we'll say, the residuals are somewhat right skewed in the histogram. So normality is not looking great. Honestly, the one outlier, because its residual was only, like the studentized residual was about 2 in magnitude, that one wasn't too concerning. And the influential point also wasn't super influential. Like it was still less than 1, the Cook's D. Sometimes you can have a Cook's D that's as high as like 12 or something. So that was really not bad. But this normality is starting to sort of pile on concerns about the model here. Let's look at homoscedasticity, so equal variances. Again, we check this in the same way as before, looking at the residual by predicted value plot in the SAS output. So here, okay. And remember, we want a constant vertical spread going from left to right in the residual by predicted value plot. Is that what we have going on here? No, right? So how would we describe this pattern? V-shaped. Yeah, V-shaped or like, yeah, fanning. So it's, if we draw, it's fanning outwards. Like what this means is that for bigger predicted values, our model has worse predictions. When it's sort of like the implicit assumption is that your model's performing the same, regardless of what it's predicting the value to be. The accuracy should be roughly the same, but that's not the case here. So yeah, we have an outward fanning pattern, which if we look at here I give some examples in the guide document again. So it's kind of like we have this right here, this outward fanning, which is heteroscedastic. We would say it's not homoscedastic. And anytime you have a right skewed set of residuals, it is very often the case that you see this outward fanning pattern. Like it is so boringly predictable now. I've seen this in so many real data sets. It's always like, oh, it's right skewed residuals. Wonder how homoscedasticity is going to look. Yep, it's outward fanning. And that it's because it has to do with like the nature of the variable being point values, and it's something that's non-negative and it's always positive. There's like theoretical reasons you can show like the variance is always going to get bigger. Like it's known for variables like that the bigger the value is, the bigger the variance is for things that are non-negative. So it's not surprising, actually. Okay, so yeah, 0 for 2 on the assumption checking here. But we'll just continue on anyway. So a new assumption that we did not check for ANOVA is that we need the residuals to be independent of the predicted values. Okay. So here, I'll go to the guide document to show what I mean here. Okay. So I give some examples that show in like the top row here, these all have issues with homoscedasticity. In the bottom row, these are all homoscedastic. So homoscedasticity is fine, but the left one is not independent residuals. And the right one is good. Like the assumptions are met for independent residuals. Okay, so the idea is here, if you look at the vertical spread, it's fine. But the problem is, if you know the predicted value, it's informative of what the residual is going to be. And that's a problem for regression. So like here, if the predicted value is smaller, the residual is almost always negative. Your model's almost always overestimating the value. And then if your predicted value is big, the model's consistently, because these are the residuals, your error, the model's consistently overestimating. So these should be independent of each other, the residual and predicted value, and that's violated here because you could draw a straight line relationship here. They're predictive of each other. And it's not always that a straight line relationship can violate this. So you could look at something like, oh, the correlation between the residuals and predicted values should be 0, but that only gets at like straight line relationships. So you can also have it be violated. Like this is a common thing to show up in data where you have this quadratic pattern. And that again is still problematic. Knowing the predicted value gives you a pretty good guess of your error, of your residual, which violates model assumptions. So yeah, this can happen. Like examples of where this maybe happens. Like maybe you're predicting health outcomes of people using their BMI. Let's think about that. Or maybe you're predicting like their, yeah, something like you're using their age. Okay, maybe you're using someone's age to predict their BMI. Okay, so for like really young people, maybe you do worse. And then for really, really old people, your predictions do worse. And then middle-aged people, your model tends to do pretty well. That would be a problem here because you're not having consistent performance across the whole data set. There's like systematic differences. And then you can also even have this, I've seen this before as well in real data, like a sign relationship, like this oscillating pattern, which again, it's still because you can use the predicted value to inform you about what the residual is going to be, that's a problem. It violates assumptions. Okay. All right. Nearly always what this means is that there's an additional predictor that's missing from your model. Like you're not incorporating some group level information. Like I mentioned, like the age of the participant being something important, like that needs to be an additional predictor in your model, probably, if you see something like that. It's difficult though to fix because you don't always know what the missing variable is. Like it's not like you always have that in your data. It might be something you're unaware of. So long story short here, how does it look? Okay, so in this data set, can we use the predicted value to give us a good guess of what the residual is? Does it seem like a predictable pattern? No, actually. So this is the one assumption that is met here. Like it's heteroscedastic, but if you know the predicted value, I would say, no, you don't have a pretty good guess at what the residual is going to be. It, like if you look here, it's like, well, it could be really negative still. It could be really positive. Yeah, you don't know. So actually that assumption is met. Surprisingly enough, because all the other ones were violated, but Right. Okay, and then lastly, so any questions on checking that independent errors assumption? I think that's the trickiest one. But okay. Then lastly, we also need that there is a linear or straight line relationship between X and Y, which in my opinion, the best way to check it is to just look at a scatter plot of X and Y. So like right here, can you just imagine a straight line going through it? Does that seem like that gets at the general trend in the points pretty well or not? Okay. Yeah, here it does not, I don't think. It's not the worst, but no matter how you draw a straight line through here, you kind of miss, like this does okay. But you kind of like, yeah, you're under predicting over here, over predicting in the middle, maybe under predicting at the end. Okay, it's not really getting at it very well. But again, I've seen worse, I guess. The textbook, which I was not aware of until I taught this class, to be honest. One of the textbooks for this class says you can look at the residual by predictive value plot, and if there's no apparent pattern, that also suggests that there's a linear relationship between X and Y. But I kind of disagree with that a little bit, because I felt like here there's no predictable pattern, but yet when you look at the scatter plot, when you look at the scatter plot, I would say to me that's non-linear. So I would disagree a little bit that that's a good way to check that assumption. We'll say we'll check the scatter plot between X and Y. That's what I would suggest. Okay, so we'll say there does not appear to be a straight line. And when I say like cite, I say cite specific evidence to support your conclusions. I just want you to say like, I looked at the scatter plot. I just want you to communicate that you know like which diagnostic plot you were supposed to be looking at and what you were trying to look for, a straight line relationship. Okay. And so just like ANOVA and the t-test, it's all or nothing with the assumptions. Either they're all met and then you're good to go. If at least one is violated, technically the model assumptions are not met. So here, we'll say overall, not all model assumptions are met, but we proceed, this is what I always say, for the sake of the problem. Because we're in school. Yeah.
Would you ever give us a question on exam that like normality is not met and you would want us to do that?
Yeah, I would, if I ever did that, I would like make clear like this, where I say like, even if assumptions are not met, like, yeah, I won't like trick you. Although I won't say other professors won't do that, but yeah, I won't trick you with like assumptions are not met and then ask you a bunch, but you shouldn't have even answered them. Yeah. I have had that before though in classes, so be wary in other classes, but I won't do that. Yeah. Okay, so let's get the estimated slope here. Trying to get the beta hat symbol to copy. Okay. Okay. You ever want like the Greek symbols in Google Docs? It's pretty nice in case you're not aware. They have this like insert, what's that? Insert special characters. And you can like draw it, which works. It's kind of nice. Like, oh, I want the beta. And then there you can get the beta like that. There's no beta hat. You have to like insert the beta, and then I think you can, if you want to add a hat, it's like, how do you do that? Well, you can copy it from the guide documents because I did it at one time. Yeah, I can't remember how to insert the hat right now, but anyway, so, and you can also just write, like if you ever want your homework, you can write like beta hat, and I'm okay with that. And the estimated slope is beta hat 1 equals, okay, so we get the estimated slope from the SAS output. Okay, right here, this table. This is the table that has the regression estimates in it. Okay, so we get the estimated intercept right here is given by the row that says intercept and then estimate. And then here it'll say the name of your X variable, your predictor variable, and then it'll give the slope for that predictor variable. When we get to multiple linear regression, where you can have multiple predictors, this will look the same, except there'll just be another row underneath, and it'll say the other predictor variable's name, and that one will have its own estimate. But right now we just have one predictor. So it gives you the estimate. This is the p-value for testing if the slope is 0 or not, which is based on a t-test, actually. We'll talk about that next week, not today, but right now we're just getting the number, the numeric estimate. So we have it's minus 0.59. We'll just give it to 2 decimal places. Okay. And note that that's negative, which is the same sign as the correlation coefficient. If you look at the correlation, it was minus 0.7. The sign of the slope and the correlation coefficient will always match each other like that. So interpreting the slope in context, let's see. Okay, here's again where I give a blueprint interpretation in the guide document. So let's copy that. Okay, so for every 1 unit increase in X, so instead of saying unit increase in X, what should we say here? Yeah, for every 1% increase in a letter's relative frequency. So we always say increase for this first part, even if the slope is negative. Every 1% increase in a letter's relative frequency, we expect, and then instead of y, we'll say yeah, a letter's Scrabble point value. And then do we say increase or decrease? Yeah, decrease. To decrease by, and then we say decrease, which takes care of the negative, and then we just say 0.59 points. I know a concern, I've noticed this like every semester, I think it's consistent. It's common for people to be concerned about this like not being a whole number, even though in this context, like Scrabble letters have whole number values, right? But when you're giving a slope interpretation, that's okay. Because you're talking about the expected increase or the average increase. Okay, so we're not saying that like a letter would ever have a fraction of a point, but we're just talking about the general trend in the increase, the average increase. So that's why it's okay to have decimals. Certainly, maybe if you're like trying to predict the Scrabble point value for a new letter, maybe you would get a predicted value and then round it. That's fine. But you know, the interpretation will keep in decimals. So let's do a similar thing for the intercept. All right, so the intercept we denote with beta 0, beta hat 0. And what is our estimated intercept? As we look at the intercept column, it's 5.64. So right there. And we'll say, yeah, intercept. Oops. And then here I give a blueprint interpretation as well. And then instead of y, just like last time, we'll say expected value of a letter's Scrabble point value given that x equals 0. And instead of x equals 0, we'll say given that And then we replace beta not hat, beta 0 hat with. So that would be really hard to play that letter in Scrabble, right? Because it's saying it doesn't show up in any word ever. Impossible to play that letter, right? So does that make sense in this context? No, and why is it nonsensical, I guess? Right, that letter doesn't even exist, right? So it was outside the scope of our data set is the key thing there. So no, because that letter does not exist and is outside the scope or range of our observed data set. And since range, I'm using range in like the everyday language range there, so I guess I'll say scope. And so what do I mean specifically by it's outside the scope of our data set? Well, we're using the percent relative frequency to predict a letter's point value. So anytime you're making predictions or interpreting estimates for your regression model, it only makes sense to do that with x's, with predictor variable values that are inside the range of your data set that you're working with. Okay, so like in the Scrabble data, we have the whole data set, so we can look at it here. Or I printed it above. Let's see. I think, yeah, right here. Okay, so we have like the percent relative frequency. So let's see like what's the lowest. Looks like 0.15 for J. That's seeming pretty low. Oh, Q is even less. Okay, I think Q might take the cake. No, Z with 0.07, I think. Yep, okay. So Z is the least, it's the most difficult letter to play in Scrabble, must be. It seems like at least. So what this means, this is the lower bound for our X. It's the minimum X value in our data set. So we should not interpret predicted values, or in this case, like the y-intercept, because it's below this minimum X value in our data set. Okay. That's what we call extrapolation. Okay. So let's see. I'll pull up ChatGPT. ChatGPT is very good at simple linear regression, I found. So like, let's see what ChatGPT has to say about that. So or what is extrapolation in simple linear regression? Let's see what it has to say about that. Oh, maybe it's not doing so great. Oh, I misspelled extrapolation. Extrapolation. Oh. Okay. It's been a little slow, but so maybe we'll just take my word for it. So extrapolation means getting a predicted value that's outside the range of your observed X's in your data set. And in general, it's not a good thing to do. You can't rely on estimates that are obtained that way. Certainly, in my opinion, I don't think it's necessarily like a hard line drawn in the sand. Like if you're really close, like in this case, 0, it's right here. So yeah, it's below the point in the data set, although it is quite close. Like it's very close to the edge of the data set. So technically it's extrapolation. But in my opinion, it matters like how close it is. in this case, it's still close to the other values in the data set. Like if you had a percent relative frequency of like 25%, so it's like way out here, you should not get a predicted value for that. It wouldn't be reliable at all because your line was fit on these points and does not necessarily, you can't assume that trend continues. Okay. This is like a common, another very common misuse of linear regression. Like people like to do it with time being the x-axis and then some other variable like inflation, right? Like they say like, oh, on average, inflation's increased by maybe like this much every year for the past 3 years. So if that trend continues for like 10 years after, inflation will be at like 2000%. So why is that estimate like really bad? Well, it's because that's extrapolation. Like you can't go way outside the range of your data set and assume the trend will keep continuing. That's often not the case. You can only describe within this range of observed values. Okay. So let's see. Yeah, we said that. Okay, now we can give the estimated model. Let's see how many bullets we have left. I know we're out of time, so. Oh man, we only had those 2 bullets left. Well, guess we'll get to that next week. And yeah, so have a good weekend and we'll just pick up here next time.